Okay. Okay. So I welcome you all again to this GAN course on day 9. So today there is a tutorial, and in this tutorial I have formulated 3 or 4 example for you. Those are very simple. One is the based on the filtering. So because you need to measure the response from the structure using sensor, so it is inevitable that there will be some noises in the sensor data. So you have to deal with filtering, right? So it should be useful to you if you know how to filter the data. So in general we use high pass or low pass filter depending on the nature of the data and what response we want to keep and what response we want to discard. Okay. So then I will discuss about the FFT, application of FFT, which is also very important. Sometimes time series data don't give the actual signature or desired signature that you want to look at. So you have to also look through the frequency spectrum of the data. So you have to convert the time series response to frequency response, okay, to check what was the response at a defined interval of the frequency. Okay, so FFT, first Fourier transformation, is performed to convert the time series data to frequency domain. So instead of time versus some amplitude, you will have frequency versus some amplitude. Okay, so it will reveal the dominant frequency contribution for a particular signal. Okay, then I will be discussing about like formulating the appropriate covariance or variance matrix for Bayesian formulation. Probably all the time we assume that noise is white noise because it is very simple to model, but in reality most of the time you will see it is not white noise, either it is correlated. Yeah. Okay, let's start with the first one. Okay. So the first example is high pass filtering of musical signal. So your task is to implement a basic digital music synthesizer and use it to play a traditional song. Then specify a sample rate of 2 kilohertz. Okay, 2 kilohertz means 2000. You have to write in MATLAB. Okay, and plot the spectrogram of the song. You can also play the song in your laptop. Okay, so first you proceed with the writing the sampling frequency, which is 2000 kilohertz. So 2E3 in short you can write. Then corresponding time you can calculate. If this is the sampling frequency, the length of the data, for example the length of the song is 0.3 second. Okay, so it will be 0 1 by fs means sampling point interval. Okay, then it is going from 0.3 to 1 divided by fs. Okay, so then fq will be having this frequency bandwidth minus infinity to minus 9 then 2 divided by 12. So note that is created is as a function of some sine function. Okay, so this is 111 then sine 2 pi 440. Okay, that is the frequency of the sinusoidal frequency. Okay, or this is a harmonic kind of function. Then 2 multiplied by fqg minus 1 fqg. Okay, so you complete writing this. Then melody is given like this: 5313550 and so on. Then you compose the song using this loop. Okay, so the note will be coming from this. Kj is running from 1 to length of melody, which is given by this, and then once the loop is completed, your song will be ready. Then if you want to hear the song, of course you can give this command, which is sound song then fs. Okay, so you compile this data and let me know whether you are getting the actual sound spectrum, which is this one. Okay, once you achieve this, then let me know. Okay, so I am going back to the coding part. If you need any help, then let me know. You see in the melody there is another melody that is incorporated as a function of ACC. ACC is kind of our noise. Okay, so we have to eliminate this later on. First you compose the sound or song, then you display the spectrum, then from the spectrum we want to eliminate a certain tone. Okay, because we don't want to keep all the things. There could be noise, there could be in data also. Suppose you are monitoring a breeze, you are measuring the acceleration from the breeze and you are getting the acceleration. So in the acceleration, by default there will be some noise and there will be some data related to the performance of the structure. So you have to eliminate the noise. For example, I have given yesterday an example of breeze solving motion where the vehicle is moving and it is producing some displacement. Now this displacement is having two parts. One is static, another is dynamic. Static because of the weight of the vehicle and dynamic because of the vibration of the breeze. So I have to eliminate, suppose, dynamic part from the total response, so that only there is a static part due to vehicle weight. Then our calculation will be more accurate, right? So this type of noise elimination or filtering is always used in real life problem. Okay, so this is one interesting example. So first you compose the song and play the song also, hear the song, how it is producing the melody. You obtain the spectrum. Okay, great. So all of you got this spectrum. This spectrum. So you hear the sound also. Output. Okay. So you see there is a melody in the spectrum as well as some other melody. also is there. So we want to eliminate some of them so that the nicer melody remains and the awkward sound goes away. Okay, some beep beep sound in intermediate sound you can hear in between. Okay. All of you got the spectrum, or there is some issue? So your next task will be using the high pass filter. Okay, for example, you can give this command, that is HONG equals to high pass. You can give any name, not only HONG, you can give any name. So the command for high pass filtering is just high pass, then the signal that you want to do filtering, in this case it is song, then at after what frequency, what is the cutoff frequency that you have to paste at. Here it is 450 Hz because it is given in the problem. High pass filter the signal to separate the melody from the accompaniment, means there is not only melody, there is another sub melody is there. Okay, so you want to remove the other melody from the main melody. Okay, then specify a passband frequency of 450 Hz. Plot the original and filtered signal in the time and frequency domain. So this signal shows the original as well as filtered time history response for that melody, and this is showing the original and filtered power spectrum, means basically this is FFT kind of thing, where there is a frequency on the x-axis and there is a power spectrum, or PSD we say sometimes. Okay, power spectral density also. Okay, right. So all of you are getting this. You can see at what frequency we are actually doing high pass filtering. It is 450 Hertz means 0.45 kilohertz, because the unit of frequency is kilohertz. Okay. So to use this high pass filter, probably you may need some toolbox, signal processing toolbox or something like that. Okay, if you are using MATLAB. Is it working in your laptop? Now again, after doing the high pass filtering, you can again hear the melody by typing the sound. Hong means filtered signal, then same sampling frequency average. Okay. Abhishek, are you able to apply this high pass filter to your melody that you got in the last slide? No? You don't have that toolbox? Is it not working? What error you are getting? Please do it quickly because we need to solve other problems. So how this is relevant to you? Suppose, as I said, I have to eliminate the dynamic component of the static component. So dynamic component means it is done to the natural vibration of breeze. Breeze is vibrating, that's why dynamic response is producing. Or as a whole, breeze and vehicle is vibrating, that's why it is producing. So suppose the fundamental frequency of the breeze is, suppose 3 Hertz or 4 Hertz, whatever it is, based on the length and geometry and other thing, specification of the breeze. So we want to eliminate the frequency above that one, right, from the response to preserve only the static point. Okay, so you have to, if you are using the high pass filtering, then you apply the high pass and then deduct it from the total response. That will give you the low pass data, means frequency contained below the fundamental frequency of the bridge will be preserved and rest will be eliminated. Okay, because it is produced by the dynamic component of the bridge. Because first frequency is the lowest, then second will be slightly higher, and so on. So bridge has lot of frequency, as you know. We can only measure some of them because we can excite the entire bridge to a certain extent. So probably few modes, 5 or 6 modes initially we can measure from the experiment. Okay. So this type of application is very relevant for application in structural health monitoring whenever you do certain type of filtering. Okay. So you have to wisely select what is the cutoff frequency. In this case, I want to eliminate another melody from this song with a passband velocity, passband frequency of 450 Hz. Okay. So whatever melody is below 450 Hz, as you can see over here, have been eliminated from the filtered signal. Okay. So if you now hear the song, you will see there is a distinct difference between the previous melody and the filtered melody. Is not it? So for example, if I do this, okay, so this is the result. Then which one? Yeah. Now you apply the filtering. Then again you play this. See, now it is filtered. Okay, so you can do this later on. Let's go to the next problem. Now, we'll be discussing about this performing the first Fourier transform, okay, FFT. So find the here, let me turn on the laser pointer. So find the frequency component of a signal, read in the noise, and then find the amplitude of the peak frequency by using the FFT. So sometimes if there is a noise in the data, so in the time series data you cannot distinguish between the noise and actual signal, okay. So you have to go to frequency domain so that you can check which one is the generated by the noise and which one is the actual frequency of the system, okay. So for example, here specify the parameter of a signal with a sampling frequency of 1 kHz and a signal duration of 1.5 second. So how to prescribe this? Fs will be 1000, T will be 1 by Fs, that is the sampling period, and then L will be length of signal, and small t is going from 0 to L minus 1 multiplied by T, okay. So you will get the time vector over here. Also you can use the same previous formula also to get the time vector. Then form a signal containing a DC offset of amplitude 0.8 and a 50 kHz sinusoidal of amplitude 0.7, and then another sinusoidal with a frequency of 120 Hz and amplitude of 1, okay. So how to write this? S is equals to then 0.8 because it is DC offset, then plus amplitude is 0.7 and then sine function 2 pi 50t and plus another sine function 2 multiplied by 2 pi omega t, okay. So what is this frequency? 120 Hz. So you are constructing a signal with a 3 amplitude. One is 0.8, 0.7 and 1. So there is a frequency of 50 Hz and 120 Hz in the sine function. Then you add some noise. 0 means random noise, which is Gaussian noise, we say RNDN, means normally distributed Gaussian noise, okay. If you use just RNDN, not only RNDN, just RND, randomly generated noise, then they may not be normally distributed, okay. They could be just a random number created, okay, without following any particular distribution. Here n suggests that it is the normal distribution, okay. So A is equal to plus some noise, okay, with a variance of 4. Therefore standard deviation is 2, okay. Now we plot this. So once you plot this signal, you will get this time series data. Are you getting the exactly same time series data? If you want to get exactly same time series, RNG default, because otherwise every time you run, every time new data will be generated. So to have the repeatable data or to repeat the same result, you have to call the similar random number. So that is possible by writing RNG1 or RNG default, okay. So once you plot this, you see this is the kind of some signal which is corrupted by noise. But from the time series data, we are not able to distinguish which one is the noise and which one is the actual signal. Is not it? So then you have to go to frequency domain to check how the container amplitude is distributed across the frequency. Now original signal is having certain frequency because it is calculated by combining a offset as well as two sinusoidal function with a certain frequency. So if you go to the frequency domain, you will see the peak as well as at 150 Hz. Probably the sine function is 120 Hz. So at 50 Hz you will see one peak, at 120 Hz you will see another peak, right? So could you do that also? Y equals to f50x, and then we will be plotting only one side of the f50, because f50 is kind of symmetric, okay, with respect to the axis. So it is having negative also positive side. Also real and complex could be possible. So we don't want to plot the entire domain of the FFT because it is repeated symmetric kind of thing. If you plot only the other half, positive side or real side, your imaginary part is just exactly same thing. Okay, so you don't have to plot both the domain. Okay, so just plot single-sided spectrum of FFT. Once you execute this command, then let me know what result are you getting. Okay. What result are you getting? Okay. Okay. So frequency is visible. The dominant frequency, that is 50 Hz and 100 Hz. Okay. Okay. So are you getting this result, right? So not only frequency component, but also you see, if you plot the amplitude, that is the mod of T1F. So this is the amplitude. So you have added 0.8 DC component, DC offset, and then direct component, and then you have added 0.7 of sinusoidal function, then 1 multiplied by another sinusoidal function with a frequency of 120. So all are visible, right? So this is the plot after the FFT. Of course there is still some noise is there because of the addition of normally distributed Gaussian noise, right? So, and this plot is the power spectrum or the FFT of original signal. In the original signal there is no noise, So it should give absolutely same frequency content without showing any kind of this type of random noise data, right? So you see it is having 0.8 amplitude, then there is nothing in between, then again 0.7 at a frequency of 50 Hertz, then there is nothing in between, then 120 Hertz, you are getting a amplitude of 1, then there is nothing, because that is the signal, raw signal, actual signal, right? So what will happen, whenever you perform measurement using some data or using some sensor basically, so you are having some raw measurement data, and that is always having some noise. There are two major contribution of noise. One is the sensor self noise. All sensor is not 100% perfect. Okay, there are some self noise coming from the sensor, and there is some ambient vibration that is happening on the bridge or any civil engineering infrastructure, right? So those are kind of, if you assume that there are white noise, means uncorrelated and independently distributed, okay, so they will look like this even if you do FFT. So frequency spectrum will reveal what is the actual contribution coming from the system, because each system is having certain dominant frequency. So in that frequency you will see certain peak. For the case of bridge vibration, right, bridge is having certain natural frequency. You have heard in physics class, probably class 12, that marching on the bridge is prohibited, right, because it could create a resonance between the marching frequency and with the natural frequency of the bridge. So that is the thing, every system, even us, if you model me using my entire stiffness and mass matrix, whatever I am having, all the parts you assemble and then model, you will see I am having certain frequency. Some person is having different frequency. Some object, this is having different frequency. So every object is having defined configuration, defined material property. So they have defined natural frequency. That is fundamental to that object. So at which it is vibrating, right? So if you see FFT of measured response from that object or body or structure, there will be definitely some peak that will be observed in the FFT or power spectral density, means whatever you are plotting in frequency domain. Okay, so that is a one simple example. Okay, next let's go to the example number 3. So you will check whether the noise is really white noise or it is having some correlation in this case. So first we will generate randomly distributed Gaussian noise, or we say normally distributed Gaussian noise or white noise, and compute it autocorrelation. So white noise means they are randomly created arbitrarily, and there is no correlation between one sample to other sample. That's why it is random, we are saying, no? Otherwise, how it can be random if it is having some certain correlation? Okay. So first you create y equals to normally distributed Gaussian noise column vector with 1000 data point. Then you give sampling frequency of 100, then time will be calculated using this same script. Then you can do inverse of that to make it column vector. Then you plot this. So there are two subplot in same plot. One is the data you are plotting, which have been generated by you, normally distributed noise, and then another is the calculation of autocorrelation of that noise, which is given by autocorrelation function, AUTOCORR. Probably you need certain toolbox to evaluate this. Economics toolbox probably, because in economics or those field lot of historical data are analyzed, and there is a clear correlation between past cell or future cell or something like that. Okay, so they use autocorrelation. So similar thing we can also use for modeling of noise in structure health monitoring, because noise is very fundamental thing that will be always there. Now you have to increase your efficiency of algorithm. So how to increase the efficiency? You have to model the noise appropriately without any further inappropriate assumption. So suppose the noise is correlated, but you are assuming it is white noise, then your model is not perfect. It will give erroneous result. So you have to understand the true nature of the noise. Okay, so that is the idea. So once you execute this, you will get this type of thing, is not it? This is the noise and this is the autocorrelation. You see, autocorrelation, there is one, then after the first sample, all are kind of zero, close to zero. That means there is no correlation between the subsequent sample with previous sample. Okay, they are randomly created. Okay, so in that case you can use white noise to model this. So whatever noise, suppose you are doing filtering first, you are eliminating the noise from the main data, then you are calculating autocorrelation like this. You check whether there is a autocorrelation function showing something. If there is some autocorrelation, then you cannot use white noise modeling framework. Like in Bayesian, I have assumed now in that is noise is distributed like Gaussian noise with zero mean and some variance. So we can use the Gaussian equation very easily, right? And covariance matrix is kind of diagonal. Okay, all are off diagonal component are zero. So very much pretty simpler mathematical framework. But when it is correlated, so how to generate correlated data? That is also a point of concern. Okay, so because we don't have now measured data, so I have to simulate something which is correlated. Okay, why not simulate the free vibration response? Those from civil background, if you have understood or gone through the dynamics, so you will see there is a response part. Okay, here you see, okay, so it will decay like this. Response is decay like this. Sorry. Okay, then it will be dampened out like this. Okay, gradually. So this response is kind of free vibration response. So you are exciting the system. Suppose you are holding a scale, okay, steel scale. Then you are stretching it and then removing this part. Then it will shake, right? It will fluctuate for some time. Then it will come to end, right? It will not fluctuate for infinite time. Why? Because of damping. So that damping is also causing decay in the structure. Suppose bridge is vibrating, one vehicle is passing. Then once the vehicle traverse completely and cross the bridge, then if there is no other vehicle, the vibration of the bridge will dampen out and it will follow this type of scenario, okay, free vibration. So if I want to create this vibration mathematically, there is an equation. Suppose U is the response, it will be e to the power minus xi omega n t. Xi means damping ratio, omega n means natural frequency at which it is vibrating, t is the time, then there will be some u naught, okay, then cos of omega dt. Omega d means it is the damped natural frequency, because every structure is having damping, so we need to also calculate damped natural frequency. Damped natural frequency is nothing but omega n, then square root of 1 minus xi square, okay, this square. So plus there is some function, okay, u naught plus p naught means initial displacement initial velocity, then some omega n, right? Yeah, then there is something omega d. Yeah, omega dt. Okay, this type of equation is there. If you solve, okay, free vibration response with damping. So why not write a equation in MATLAB or Python? Just varying the time. You vary the time, you specify the xi, some damping, probably 5% damping. You can assume every structure is having 2 to 10% damping. Okay, means xi will be 2 to, if I assume 5%, so it will be 0.05. Value will be 0.05. What is the omega n? Omega is the natural frequency. You can assume natural frequency as probably something like, you can assume 10 Hertz or something like that. Okay, just to start. Okay, then omega d you calculate and you vary the time. For example, 10 seconds. For 10 seconds you want to calculate this. Okay, that could be possible. So it will produce this type of response. Okay, let's do that. Okay. This is the code that I have written. So you see, xi stands for damping ratio, which is 5%. Then omega I have taken 10 Hertz. Omega is the natural frequency. Then omega d is omega multiplied by square root of 1 minus xi square. Okay, as I said, this omega d is nothing but omega n, then square root of 1 minus xi square. Okay, so this is the equation that I have been written in the MATLAB. Then you take some initial condition, u naught equals to 0.1 or v naught equals to 0.1. You can take also 0. Okay, if it is rest, initially at rest. So you can arbitrarily take. Okay, I have taken 0.1, 0.1. Then you construct this function, same function that I have written. F equals to exponential of minus xi, then omega t. Okay, you don't forget to place this dot. What is the significance of this dot? Can you tell me? It is not a matrix multiplication, it is element level multiplication. One at a time. Now, t, suppose t is okay, here I forgot to write time. Time is for example 10 seconds. Okay, so you vary the time, you create a vector from 0 to 10 seconds with a sampling frequency of 100. Okay, so first will be 0, then 0.01, then 0.02 up to 10 seconds. Okay, so it will create 1000 data points, is not it? So you just, for each of those time, when t equals to 0, when t equals to 0.01, when t equals to 0.02 and so on, you calculate this function. Okay, so that will give you this function ft or ut. Here I have written ut. Okay, so once you get this is the function ut is equals to f of time. Time I forgot to write over here, so why not I just show you the actual code. So if I open this one, so are you able to follow this? Yeah. For creating the Gaussian noise, right? I have mentioned time. Then you create this one, xi1 0.05, then W equals to 10, then WD is W means omega multiplied by square root of 1 minus chi square. Then you give this, then you call the function, then you get this ut. Okay, then you add, first you check without adding the noise. Okay, okay, first you check without adding the noise. Okay, what is the result? So let me run this. Yeah, is it visible to you? You see, this is the free vibration response. The left side plot is the actual free vibration response, and if you calculate the autocorrelation, you see there is a same kind of trend because all are correlated with each other, right? Because this is a function that has been generated with this e to the power minus chi omega in t, means they are all correlated kind of. There is a and this, so one time with the subsequent time. Okay, so therefore this cyclic pattern is there, cyclic pattern, free vibration. Okay, so that means they are not randomly generated, right? They are interlinked. First it will go like this. See the vibration, when there is a vibration about the mean, it will fluctuate like this, like this, like this. Okay, so you see the about the mean, it is first fluctuating, then dampen out because of the damping. If I remove damping now, so it will not dampen out. For example, if I make this 0, then what will happen? See, the response is not decaying because it is free vibration response. So no one can stop that vibration unless you apply certain external force. Okay. However, there is a autocorrelation. Why? Because it is sinusoidal function. Sinusoidal function, you see, there is a cyclic pattern. They are related. They are not random, right? So this type of exercise you can carry out to understand the dynamics more appropriately. Okay. Now if I make it very highly damped, 10%, then what result you will get? See, if the damping I am increasing, the more damped structure means it is coming to rest very quickly. It dampens the motion. Okay. So this type of thing you can select. Let's choose 0.05, that is 5%, and of course if I increase the natural frequency, suppose it is 20 Hertz. 20 Hertz means it is very stiff, right? It is fluctuating very rapidly. Okay, so if you do that, see, very stiff, so you are getting this type of scenario. Okay, now if I make it very flexible, suppose 2, what will happen? It will take lot of time to complete one cycle. Flexible means it will take lot of time to complete one cycle. So frequency is nothing but how much time it is taking, right, to complete one cycle. Okay, so you see 10 seconds is not enough. Okay, so for example, if I take 5, then also you are seeing still it is vibrating. Okay, so let's keep the previous combination, which is 5% damping and 10 Hertz natural frequency. So this is the result we are getting. So now this is the actual response, theoretical response. Now if I add some noise to it, then what will happen? Oh. See, I have added some noise to the signal. So you can see there is a free vibration decay, but there is some noise. This type of thing you will see in the real measurement. Suppose you are running car and then measuring the free vibration of the bridge, because you want to estimate the frequency, natural time period, or mode shape or damping ratio of that particular target structure. So you will have this type of free vibration decay, but with that there will be some noise, which is like this. So now also, if you assume the noise present in the data, so of course you can, first you need to do filtering of the noise, right? And then you have to apply the autocorrelation to check whether the noise that have been added is actually correlated or non-correlated. In this case, I have added white noise, but I have calculated the autocorrelation to the total response, right? That's why it is showing this significant correlation among the data, right? For example, instead of white noise, this random noise, if there is some other method to generate autocorrelated noise and then you add this, then probably you will see similar kind of pattern if you apply the autocorrelation to noise only. So here I have, because I wanted to show how to calculate the autocorrelation function and how to check whether the noise is correlated or not. So that's why I have demonstrated this by applying the autocorrelation to the entire signal. But your process would be, first you remove the signal, remove the noise from the signal, then you check whether the signal or noise that is there is correlated or uncorrelated. Based on that, you apply a mathematical framework to model that noise. If it is uncorrelated, then you have to assume uncorrelated noise mathematical model. If it is correlated, then you cannot assume that it is simply uncorrelated and diagonal parts are there or other parts are kind of zero, right? So this cannot be done. So this is one of the examples that you can do. So probably we are reaching end of this session. So just before concluding, so you can model any type of structure in MATLAB just by using finite element code. Okay, just you use the basic finite element code, how they are connected to each other, member and joints, right? And then what is the property of each member, what is the boundary condition, which one is free, which one is kind of fixed. So that way you can construct this type of K matrix, stiffness matrix, which is very large matrix, 12 by 12 matrix for space frame. Okay, if you are coming from civil engineering background, your K matrix for space frame means most complex scenario will be 12 by 12. Okay, then you can also calculate the M matrix, which is the mass matrix. Of course, if you assume the lump mass model, then your mass matrix will be diagonal. If you assume the consistent mass matrix, your diagonal will be fully populated. Okay, so by doing so you can get the K and M matrix. Then you apply the boundary condition, means restraint degree of freedom you eliminate from the total matrix, and then you do the eigenvalue calculation, means natural frequency identification. Eigenvalue means you solve the eigen equation and get the eigenvector and eigenvalue. From the eigenvector you will get the mode shape. From the eigenvalues you will get the frequency of the system. So this type of thing can be done. I'll just give you a simple illustration. Suppose this is the bridge that I discussed in one of the lectures. So this is the truss bridge that I model in MATLAB, and then I can also plot how the breeze is vibrating in that particular mode. So for example, this mode is number 2, it is the bending mode. As you can see in the SSI plot, probably in one of the slide you could have seen, it is the bending mode. So if I change this to 4, it will become a torsional mode, because I know this, I have done this. So you will see the twisting. You see the twisting of entire breeze is happening. Okay. So this type of thing you can do. So by writing some code, you can do many calculations. Not only simple application of some training and testing the data, but by using fundamental thing, you can do many other things. Okay. So you should explore those also. Okay. So I am ending the session over here. If you have any doubt, let me know.
Instead of vehicles, if there are trains, very trains of terms, so we can also do that for jetties and modular networks.
Now for any structure you can do similar modeling. There is no constraint on that, because you need, I think, have you used the finite element software, any finite element software? There is ETABS or StatPro or SAP or ANSYS, Abacus, there are many. Midas. So in those finite element software you can do modeling of different type of structure. Even the mechanical person will model the vehicle, the aerospace engineer will model the spacecraft, okay, civil engineer is modeling the building, bridges. So there is no limitation. So fundamental things remain same. So you have to construct the K matrix, stiffness matrix, any dynamics problem. As I mentioned, there are 3 parameters. One is the mass, inertia, always there. You see when you are traveling on a vehicle and then the driver apply a brake suddenly, you will tend to fall down because of the inertia. So that is always there. So inertia tries to resist the motion. It will wants to have that same motion that it is enjoying probably, right? So if you don't apply any external force to the body, it will be in that motion only. If it is on rest, Newton's law says that it will be rest forever. If it is on motion, it will be on motion forever if there is no other external forces there. But there is damping always there. Okay. So mass is there, damping is there, and stiffness, because there is a material, there is geometry. So all those things should be taken care. So stiffness takes care of that thing. So these 3 parameters combine a system. So if you model those things for any system, you should be able to model that object or body or structure. Okay. And then do you similar kind of thing. If you want to monitor something, you place the sensor, you record the data, you process the data, and try to extract this significant or some kind of fundamental signature that is relevant to you, also that are damage sensitive features. If you want to detect the damage, is not it? So I have explained this probably yesterday very rigorously and comprehensively. There are all framework is there, cycle wise I have mentioned. So you can apply to